So, Professor Auffarth, we are excited to hear your lecture, and I hand over to you now. Please go ahead.
Okay, yeah, Mr. Banchok, thank you very much. And ladies and gentlemen, wherever you are and how early or late it is, wherever you are, it's a pleasure for me to give this webinar and share with you our experiences with the Pentacam AXL Wave. As I already mentioned, we have a long tradition in working on this field in research in my clinic, and also working with the Pentacam, the different stages and development and generations of Pentacam. And we actually have reached now a point where the Pentacam more or less can give us an enormous amount of information. And the question is, do we have to buy several machines, or can we get everything in one machine, and is it worth the investment? These are these are my financial disclosures. As you can see, we work with a lot of companies together and doing a lot of research here, but also funded independently. When we talk about the developments in diagnostic, we really have to say that there's enormous development in the last couple of years. And we can almost look at this, that we have a kind of paradigm shift in science in the last couple of years through these developments. But what is a paradigm shift? Normally, we would consider a completely fundamental change in the basic concepts of some ideas in scientific atmosphere surrounding as a paradigm shift. So from the world as it is to the world as a globe, so to say. But this may be not really the right term to talk about a machine like a Pentacam, but there's another terminology where we talk about disruptive technology. And this is something which is very important because it shows how big of an impact a new development has in the daily work we do, in the way we perform medicine, do medicine, depend on things. And you all know that we have a lot of disruptive technologies which are discussed nowadays, artificial intelligence, all kinds of stuff that we have. And one really good example in this case is the simple smartphone, which normally for us today is so normal that we don't even see that this is a huge computer that is not only a telephone, it is a digital camera, it's a video camera, it's a navigational system, it's even a PlayStation or a music MP3 player. It's a calculator, it's a watch, it's an alarm clock, it's an answering machine, it's a dictaphone, and you can add a lot of apps, and your phone is really a smart thing that can do a lot of things. But nevertheless, we still have a keratograph or a tomograph or an IOL master for measuring axial length. So what we need is more or less a smart diagnostic team that can, or system that can put all these things together so that we can do one measurement that more or less tells us everything we need to know, at least for a wider group of patients. Of course, you cannot put anything in it, but you can really get to a point where you have quite a bit of information done actually in only one measurement or with one machine. So why is this a challenge? I mean, if we look at this, for example, from my perspective in a university clinic, it's not that we are always free in what we're doing. We are budgeted. We are limited sometimes in space. We are also limited in terms of human resources, or we have, like we at the university, have continuously new medical staff or medical students, technicians. So you have to educate them on a frequent basis. It's not like everything is only in one hand forever. So the logistics, if you have a high patient's volume or the patient's flow itself, is very important in a bigger setup. And even if you're a busy person in a private practice, these are also the topics you're dealing every day with. How can I get most efficiently my patients through my clinic? How can I be sure that I won't lose any information or that I capture all information I need? And on the other hand, patients look at the setup that you have. So there's competition between different practices or different clinics, who has the most modern or most accurate or most reliable tools to look at the eyes of our patients. In Heidelberg, dealing quite a bit with the area we're covering here. So any kind of corneal interventions, keratoplasty, DMAC, DSEC, all the corneal operations we do, including, of course, corneal refractive surgery, not only LASIK, also inlays, all these things. Cataract surgery, of course, is a routine, but refractive cataract surgery or refractive lens exchange, especially with multifocal, EDOF lenses, toric lenses. This is one of my specialties where I put a lot of effort in and where we are doing also a lot of studies. Faking IOLs, or iris fixated lenses, how they are positioned in the anterior chamber is an important topic. Nevertheless, a big clinic has anything else, glaucoma, vitrectomy, all kinds of surgeries. And if we go back to the cornea, also keratoconus screening or follow-up when we do the cross-linking treatments. So what we need then is that on the one hand, whatever device we have, that it is easy to set up, that we have regular service and software updates, and that my staff, the technicians or the doctors who are using this, have a steep learning curve. We cannot afford them to experiment several months with the machine until they understand how to work it. So it must be self-explaining, and it must be easy to understand, even for the patient, sometimes just to show him something. We need objective criteria for quality control, easy, maybe with one quick view interpretation of maps. So the way you display the data should be also very, very good. Behind all this must be validated examinations, numbers, that you know exactly what you measure is also what really is important here. In order to have a good logistics and good patients flow and so on, we need a standardization of examination routines. Not having this as an exotic instrument that you use from time to time. It must be standardized, and must also give you the possibility, on the one hand, to get a standard service, but also to have a customized approach for the individual patient. And quality management is extremely important before surgery, during surgery, and after surgery, especially if you have a high patient flow. It is very easy that you miss something, and then at the end, you ask yourself, oh, how could that happen? So this is a very important thing. What can the Pentacam AXL Wave do? If you look just at the hardware, it's a Scheimpflug tomography. It's an optical biometry machine, can measure the axial length. We can measure the total eye wavefront and also split it off at different optical parts of the eye. The objective refraction, both of these things are based on Hartmann check technology. We also can do retroillumination images, and also combined with the Scheimpflug approach, a look at the lens, not only how opacified a cataract is, also how an intraocular lens is located inside the eye or oriented, if you look, for example, at toric lenses. So we have a lot of possibilities that we can do here. For the clinical application, the first thing is that we are screening. We want to make sure if we do a cataract or a refractive or another procedure, that we don't miss any comorbidities that will interfere with that, or that we miss, for example, a keratoconus. So early ectasia or just the risk for that is very important, and the long-term tradition of the Berlin Ambrosio features inside the Pentacam is here very important, especially the ABCD KC staging and progression setup that we can see there. For the corneal refractive surgery, we look at the different features in the cornea, on the wavefront, and so on, which should be displayed in a way that you can see it directly. And the interesting thing is also having a Scheimpflug system, we also get anatomical information where we can do kind of planning of putting a faking intraocular lens in. We can see how well it will fit in, or what may be the challenges, or how is the sizing, wide to wide, and so on. The cataract surgery, we always have the problem that we sometimes have to put several measurements together, especially in special cases, If we want to do a post-LASIK cataract patient and do IOL calculation and selection, here everything is built in, including the corneal examination and all the adapted formulas for post-LASIK or post-PRK patient. The updating of the new formulas is always important, and a huge IOL database inside the system is also, especially for high volume surgeon and premium lens surgeon, a must, more or less, in a system like this. When we compare the different developments of the Pentacam HR, of the Pentacam AXL, now of the Pentacam AXL Wave, there are new applications, as you've already heard, objective refraction, then also for more or less education for our patient is a visual performance analysis. So we can show the patient pre-surgery or pre-operatively possible reasons for its visual disturbance. If it's a cataract, if it's some corneal aberrations or an astigmatism or presbyopia or whatever, we can objectify that and show that. Post-surgery, when we do the quality management and we want to make sure that everything goes smoothly, we can also show the patient if there is an issue. PCO, you can display objectively. You can also see if a lens has decentered or whatever. So we can do that and show to the patient. And the IOL power calculation was very much enhanced in this system now, especially for every corneal shape or corneal changes. So the benefit of a system like this is, on the one hand, standardization and the time and space you're saving. You don't have 3, 4, 5 machines, and patient has to go from one machine to the others. One setup, one push of a button, and you can get the data you need. If you have already a Pentacam, you can import the data. You are not lost. And the Pentacam software is extended and updated all the time. So this is a very good thing. Let's have a look now how the machine works. Are we doing an examination here now? You see that we're trying to focus on the pupil, and the display will tell you how to move, and then here you see the measurement already released. What you see here is more or less what the patient is seeing. Also the distance he is looking at. You can get near target or distance target. So aberration has already been done, as you can see here. And we see some of the data, but we will have a summary. Now retroillumination, now axial length is already in process. So we're doing now the axial length measurement. Next is tomography. You see here the measurement is almost done. Here, very nice peaks. Excellent. So now shine field tomography is done. You know how this measuring head is going around the eye. You see here the display. And now you can put all the data together in an overview. This takes momentarily after everything has been calculated. And now we see the tomography data, and now we will go and get the whole picture. So now on one page, we have almost everything. We have here the refraction of the patient. We have here the wavefront. You see the spherical aberrations, the entire high order aberrations, corneal aberrations. You see the visual performance in terms of this display here. You see here the axial length. You see all the measurements, and you see how accurate they are. You see also the signal noise that you have. You see here the retroillumination photo. Here the sagittal curvature, and you see here the keratometry, corneal thickness, and here chamber depths. Everything is here on one page, which really gives you a total overview on one screen of the whole patient, so to say. And then you can go into detail, look at tomography more, even check corneal internal total aberrations. Everything can then done in the sub menu. The benefit is from this routine that it, as you have more or less seen, this was live measurement in less than a minute or so, or 1.5 minutes, and most of the time was actually for calculation, not for already looking into the device. You also get a direct check if the quality of the measurement has reached a certain limit and is acceptable. That doesn't mean that a measurement is not true if it hasn't been, cleared through the QS change, but nevertheless, very, very high standards are put on here to make sure that it's almost impossible to have a measurement that is completely out of range. We have seen that the fixation targets can align itself and can tell you where to put it, especially if you have patients that have some fixation problems. And for the examiner, this is really almost foolproof to do it. And you get the important parameters directly shown. You can actually also, if you want, customize a little bit what you see on the screen. So we have the whole information displayed. So that looks all very nice, but the question is it really so good? And how does it compare to what we have so far, or what is the gold standard, or what we consider as a gold standard? And will it give me additional value only by the combination of different things, or will it give me also additional value because of the accuracy, how the machine is measuring? So let's go for the first fight. Let's see if the Pentacam AXL Wave is as good as the IOL Master, or how they correlate with each other. We've done a study, so we're comparing here more or less a coherence interferometry for the axial length measurement, which is implemented in the Pentacam AXL Wave, with the IOL Master 700, which is the newest model, which is using now axial length measurement by swept source OCT technology. So let's see how this goes on. We have an ongoing study so far already. 225 patients, phakic eyes planned for cataract surgery have been evaluated. We didn't do any exclusion of ocular pathology, so there were also patients that had very thick cataracts and so on. But in order to really make sure that we have 100% good measurements, we use the inbuilt quality control system in both machines. So, for example, in the IOL Master, if you have a measurement and this sign is displayed on the side, that means that this is a not 100% correct measurement, or that the measurement does not live up to the highest quality standards IOL Master is supposed to do. The same is displayed in the Pentacam. Here we see an OK. So if OK is displayed, this measurement is OK, so to say. A lot of people overlook this little sign on the IOL Master, and it's not so infrequent, I have to say. That doesn't mean that the measurement is not correct, but the machine tells you that there is some uncertainty in it, or some elevated signal noise ratio that should alert you to make sure if this is plausible. So the machine, and here's the limitation the IOL Master can measure, is axial length, corneal radii, anterior chamber depths, and wide to wide. And these are the parameters we're comparing here in an average group here, 64 years. Most of them are cataract patients, but there were also some refractive lens exchange patients, as you can see, or some juvenile or traumatic cataract patients. So if we look at these data, and if we really go for this quality measures that you don't have in OK or on the other side for the IOL Master, and the interesting thing is that in almost 90% the Pentacam had OK values, and only in 81% in the IOL Master. Maybe people will say this is not, I don't understand that, but really look at your IOL Master printout. Quite frequently you have one or the other measurement that is not 100% okay for the IOL Master's quality system. And in this case, we had to exclude this measurement and only took those who had 3 identical good measurements that were okay. So this is quite interesting to see that, because the IOL Master, of course, has a lot of development over the last years, and compared especially to the axial measurement of the Pentacam. So I was quite satisfied with that when I saw that. If we then go and look at the values, essentially they are the same. Yeah? If you look at this here, 23.5, 23.44, and also the standard deviations, the so-called covariance, 0.02 millimeters, we are reaching here an area where there's no relevance anymore in terms of does that change the IOL calculation if you have a slight difference here. Also, the keratometry values are identical. Anterior chamber depths, we saw slight differences here, which may be attributed to the different type of measurement with the time flux system. And wide to wide, there are slight differences. However, they are not relevant if you look at this. And statistically, as you will see now in the next slides, there were no difference. So here the total axial length, you see this is more or less one line. Yeah, there's no difference. There's a very, very high correlation. So it doesn't matter if you measure with the AXL or with the Zeiss IOL master, that the data are the same, more or less. Quite easy to say. We have different ways to look at this from a statistical point of view, especially if you look at outliers and something. And you can see here that this is a very good agreement, the so-called Bland-Altman plot, and shows a high measurement accuracy of both devices in this context. The corneal radii usually also, if you measure with one machine, will vary a little bit. This is nothing special. We've done a lot of comparative studies in that area with corneal measurement devices. This is a good correlation between two different devices. The correlation coefficient is over 0.96, so it's really good and very reliable. And your chamber depth, you see slight differentiation the deeper the anterior chamber gets, which makes sense, but still very high correlation, 0.9973. So this is identical, so to say. Wide to wide, we expect some variations, still the decent correlation. And normally we check, for example, for sizing of a lens. We're talking about 0.5 millimeter of differences may change our decision. And here the difference is much smaller. So we have a good success rate of axial length measurement, and the internal inbuilt quality control of the Pentacam AXL has a very high level, I have to say. Good correlation and agreement for both devices in almost every different type of measurement that we did. And interesting thing is, especially if you do several measurements after each other, that you have a low dispersion of values. So the reproducibility is very high with both devices. And we're comparing here a more or less new device against a very much established device. So this is a very good thing for this type of device. Okay, but we can do more with the Pentacam AXL Wave. So let's look at the next study. Here we have the competition in terms of refractive measurements and also in terms of the wavefront that has been measured here with two devices, the NIDEC and the Schwind machine, ORK. So refraction, high order aberration, spherical aberration, these are our values. And we looked at this in different patients. We looked at normal phakic cataract or clear lens extraction patients. We looked at pseudophakic patients. And as a special subgroup, because we're dealing here also with tomography machines, at phakic keratoconus eyes. So this becomes more challenging now in terms of comparing in more complicated situation. But that's why we need all these machines. So setup was more or less the same. We have three patient groups, as I just said, 3 devices. Again, 3 consecutive measurements. Only measurements that had this quality thing was okay were used. And we did in each group around 38 to 28 patients, as you can see here. Let's just look first at the spherical aberrations and phakic eyes. We have Zernica 4 here, 4 millimeter diameter. You see the ORK from Schwind and the Pentacam are the both machines that measure that here, the total wavefronts. And you can see identical values, 0.03 or 0.029. This is identical. Standard deviation similar here for the overall measurement. If we go a little bit more in detail and look at the standard deviation and also the difference between measurement 1 to 2 to 3 and so on, you see a little bit more variation actually here at the ORK, also a little bit broader and more standard deviation, at least at the third measurements here. You can see that here at the values, maximum difference here 0.051 or 0.118. So we have differences here, but in general, excellent agreement. So Pentacam is as good as this. And we see in terms of repeatability, I think even a better outcome from the Pentacam AXL Wave in this comparison here. Objective refraction, let's have a look here. We're talking now about the phakic eyes. And here we observed something we saw also in other studies, that the Schwind machine gives you some other data than you would expect. Here you see the NIDAC and the Pentacam showed more or less identical values and also similar standard deviation, whereas the ORK was like half a diopter off compared to the other two devices. Here again, blonde ointment is good. And when we look at the astigmatism, we think this is one of the reasons the ORK is measuring that in a different way, because you can see here there was much higher difference compared to the other two measurements, which were identical here in their measurements. If we go to the pseudophakic eyes, we can see again excellent agreement between the NIDAC and the Pentacam, and you can see here almost the same mean values, good correlation. ORK is again a little bit offset here, similar with the astigmatic measurements, which are seen here. It's getting better in terms of the ORK when we have more distorted corneas. Here we have also a little bit more standard deviation and variation, but you can see here the NIDAC, Pentacam, even the ORK are on similar level in terms of the mean values. Still is a little bit more standard deviation here with the ORK Schwind machine. You can see that also here in the astigmatic correction, but here we get a little bit closer in this machine. But Wave and the NIDAC machine showed very good results and very comparative. So here we can see what we just saw also in the video, a complete setup of a normal phakic eye, almost ametropic, as you can see here, with low aberrations, as you can see, normal axial length, and also very accurate, reproducible. Here the QS is okay, here the QS is okay. Tomography with all these data, QS is okay, very normal cornea. So this is more or less like an ideal patient, a picture you would put in an educational teaching book or something for the students to explain to them. And this is an image here of the retromulation feature. So not only can you see a cataract with a Scheimpflug system, where you can go to a slit and then see the intensity of the cataract, you also can look at it from a retromulation perspective. You can see, for example, cortical or subcapsular opacities much better. However, you can also look at the intraocular lens. And here, of course, it's very interesting to have, for example, a toric lens, see the markings, do an overlay with the tomography. So there's a lot of possibility here, or go into detail on PCO, on tilt, on whatever. So these are the features we have here. And I looked at a couple of patients also in terms of the consecutive measurements. If you look, for example, here at this patient with all the aberrations, this is like a 47-year-old patient, like a presbyopic patient, Caucasian from Germany region. You already see on the display that these measurements look almost alike. Yeah, you see already virtually the same distribution of the aberration, which explains to you again that the reproducibility is very high. Even different type of patient here, very young Asian patient, which sometimes have a little bit slightly different flatter anatomy to some of the northern European people. A very nice display and very competitive, comparable consecutive measurements for the right and the left eye. Or cataract patients here, 87 years old, also reliable measurements, and one display looks like the others. keratoconus, you see directly visually the situation and also the amount or the grade of keratoconus or this formation in this 53-year-old keratoconus patient when we look at these consecutive measurements. So that leads us to hard data in terms of reproducibility. So now the Pentacam AXL Wave is fighting against itself, so to say. We, especially interesting for me personally, that's why I put this slide in, is that if I want to select premium IOLs, I really have to look at certain features to have like 100% optimal outcome. I'm not talking about only 75 or 80% optimal. It must be 100% in a clear lens extraction in a patient that pays a lot of money for not only the procedure, also the implant. So the total corneal and posterior surface changes, spherical aberrations, high order, or the chord mu, which is the distance between vertex normal and pupil center. If we express that in millimeter, it's called chord mu. If we put that in degrees, we call it angle kappa. So most of you may be familiar more with this terminology, but in the Pentacam, it is highlighted or is termed as chord mu, and the dimension is millimeter. So we did here 64 eyes, patients for cataract surgery, normal eyes, in this case, no keratoconus or post-LASIK or other diseases, and around 72 years, plus minus 10 years old, a normal group here for cataract. And let's look now at the reproducibility. So looking at the total cornea for millimeter zone, high order operation, you see here the value 0.19, a very low standard deviation, almost identical distribution in terms of standard deviation, in terms of middle, and the percentiles. If you look at measurement 1, 2, and 3, that's kind of almost not distinct. It looks like a little bit that's get better the more you measure. Yeah, here the standard deviation is slightly lower than at the beginning, but nevertheless, these are very good reproducible values. The classical circle aberration is like a 4 here measured in the 6 millimeter zone. We also see a very low standard deviation, a mean value, because we're talking here about the total cornea, which is slightly over 0.27. And we see here again more or less the same distribution. We also see more measurements, means a little bit less standard deviations. This is not statistically significant, but when we measure, we get better and better results here. Angle kappa is something that is already difficult to measure, and nevertheless, if we look at this again, we have a very good standard deviation here. And if you look at the distribution over the 3 measurements, it really gets get almost identical. Especially the last 2 measurements are better than the first measurements. So again, here we have a very good reproducibility in these patients. When you have a machine like this, if you're at university clinic, you always have also a special situation or difficult situation. And one of these challenging things is, for example, if you have to measure in silicone oil filled eyes. It's not, you know already from ultrasound that the speed of sound is completely different in a silicone oil filled eyes compared to a water-filled eyes. So we know that we have problems to measure. We were very happy that we had optical methods to measure than with the IOL master, which were much more reliable. However, even those measurements have an offset. The IOL master in its current form, and also the versions before, have been adapted to that. The offset has been implemented in the algorithm to calculate that. So this is kind of gold standard. We don't have that at the moment, or when we tested the Pentacam AXL Wave, we didn't have that. So far, the idea of the study was to measure this offset and implement that now in the machine, so that we also have reliable measurements with the Pentacam AXL Wave. And I'd like to share with you how we walked through that exam. You all know that silicone oil is more used, of course, in the retinal department. We have a lot of patients which have, let's say, very nasty retinal detachments, need to get re-surgery or reattachments, and then need, in the end, silicone oil, or diabetic patients. Fortunately, not as often as it used to be because of intravitreal treatment that we have now in these patients, but still we need it very frequently, and then these patients get cataract or have other issues. And measurement through in silicone oil fili is not so easy. If we look at this, IOL 500 already, with a partial coherence interferometry, but also the 700 with step source OCT has a dedicated measurement mode, and we want to find out how can we do that for the Pentacam AXL or AXL Wave. This is setup or the aim of the study. Again, 3 consecutive measurements, you know all this from the others, and the same type of evaluation. There were no specific exclusion criteria. There was just the inclusion criteria that we need silicone filled eyes. And here we have already gathered 24 patients, 24 eyes. We could do the measurements in these patients. You see also the demographic here of the patients. In most cases, we knew actually what the silicone oil was, and it was the same intensity, 5,000 centistokes. So let's look how they came out. The interesting thing, what you see already is that the whole box plot is more or less in terms of his shape identical, just moved a slight bit to a different average value or mean value. As you can see here, the mean difference was 0.82 millimeters here. But otherwise, if you put them together, they are more or less identical in terms of the distribution. So what we do now, we use this value, implement that in the formula. You see here, as a matter of fact, a Bland-Altman analysis of the previous data, which also show you a good agreement. And if we recalculate that, incorporating this 0.82 correction factor, then we have more or less identical measurements. The mean difference is 0.005 plus minus 0.007 millimeters. So we have a very accurate measurement with this very simple approach. This has to be fine-tuned, and the algorithm is not as simple that you just put the number in and edit or take it away. But nevertheless, we already have enough data to get a very, very good agreement because already there was a very similar distribution. If we look at it percentage-wise, so we say how many percentage have less than 0.05 millimeter difference, it's already 61%, less than 0.1 millimeter difference, 82, 83%, less than 0.15 millimeter, it's like 100%. With tuning, you really can get completely equal values from this measurements. And again, here we did some more analysis with this, and we looked at the so-called variation coefficient, so which tells you a little bit about the repeatability and quality of the measurement. And here we also have more or less the same value, and it's statistically not significant between the two machines. So adding that and looking at this and can tell you that we have now a more or less agreement between the two measurements, and the conclusions actually tell you what I just said. In other words, so the machine is also ready and reliable to measure these complicated eyes. Well, one thing is to have all these data, these statistics, and if there's an average agreement, it's very good. That's something basic that we need actually to trust a machine like this. I would like to show you now some little clinical cases, not really so special, just everyday cases where we can see how advantageous sometimes a machine like this is, or how handy it is, or sometimes also why is this better than the other machine. So if we look in these cases, let's just take a patient here. He complains about vision loss, or not really loss of vision quality, especially in dimmed and dark and light conditions, especially when he was driving, bad weather. He's not so happy. He got a myopic LASIK around 20 years ago. I assume it was with mechanical microkeratome. I assume it was not like a high-tuned wavefront guided or whatever. At the time, we didn't have that, minus 4.25. He was planar, shifted a little bit to near side now, but he was already, he knew that already, that was not his really problem, but he was not happy about the reduced quality of vision. Do the Pentacam, we can see here the basic data. So we have a little bit higher order here. We have myopic shift, spherical equivalence -1, combination of spherical equivalent and astigmatism. The other measurements, axial length is normal for myopic patients, so this is also okay. The other values are okay here as well. So let's have a look more detailed. And this is what we see when we look at the distribution of the wavefront. So we have here the corneal, we have what is the internal here, and here the total. And we see that the cornea is pretty okay. Yeah, so it's not that we have here from the 20-year-old LASIK some funny aberrations inside the cornea that produces a bad image quality. And the worst problem is the lens. So we have here in this age group a combination of presbyopia and beginning cataract, which causes the problem and makes this total image look like this. Not too bad, you can work with that or live with that, but you see already the difference. And consequently, you would, for example, counsel the patient in terms of if he wants, you can do a lens exchange, put a multifocal lens in or whatever, and you have all the data already with these one measurement here. You can calculate directly an intraocular lens based on all the data that you have here, as you can see. And then if you want to do a calculation, you have already to implement that this is a post-LASIK patient, but everything is in the machine. You see here the myopic LASIK feature. Here we have the Barrett True K myopic LASIK feature. You may go for a operation correcting IOL, like the Technis lens here, and you get directly the data and very accurate. So you're already set. You can talk to the patient, and you have already a solution for his problem. And the only thing is now is to decide if his problem is so bad that he wants to go ahead for surgery, but at least he knows where it came from, and you can also observe it and see if visual acuity becomes worse, and then go ahead and do this, because you have all the information with one measurement from the diagnostic up to the treatment, so to say, in this patient. Let's see some other clinical cases. For example, maybe you have done this patient now as a multifocal or multifocal toric lens being implanted. What we would see then is also quite interesting. Here we see the wavefront of the cornea. We have a patient with an astigmatism, so it cannot be good. So the cornea isolated has a image quality issue. We correct, in this case, the astigmatism with a toric lens. You see here the little marking. So if we just measure the lens, the intraocular lens, then we also have a funny image, because here we have an astigmatic correction inside the intraocular lens, or the opposite of this. But this and this together equals this clear image, because the whole total corneal eye wavefront then produces, because of these two, a perfect image and a very good image quality. So we can really see that very nicely with the Pentacam. And we could say, okay, if we have a image like this, and then we have some other changes here, that maybe a rotation or whatever has been done. But you can see also here directly, if you overlay the axis of the lens and the tomography, that you have a good outline. Here's another example of that, where you really can measure also the offset and then can decide, does that have an impact? And also look at what zone do we have an offset. Here, for example, the central 3 millimeters are perfect. So this patient has no issue with his toric lens. Other clinical cases, which are quite interesting, is sometimes And this was one of my first cases where I looked at the refractive lens exchange patient, which were not so happy after surgery, and then we recalculated a couple of things, and I will walk you through this case. So a 55-year-old male patient, and he came in the clinic. His uncorrected distance visual acuity was 0.6, 0.8, or 20/30, 20/25. It's not so bad, actually, you have to say, but his uncorrected near acuity was fairly bad. It can be explained why he was not happy with that. And he didn't want to wear glasses. He used to be slightly hyperopic and never have worn glasses. And now it was really getting on his nerves that he needs at least a near addition of 2.25 or so. And the thing is, with a little bit of astigmatism and hyperopia in both eyes, he had a perfect visual acuity, 20/20, 20/16. And also the near acuity was very good. So if you want to do surgery to change this to this, you must be more than accurate. I wouldn't recommend it in every case, especially if the personality of the patient is a little bit strange, but nevertheless, here we have a situation where you have to have success and everything must be perfect up to 1/4 of a diopter. So our usual way we do this at the time was to do the IOL master, do an IOL calculation. In this case, we decided here for the left eye to use 20 diopters for ametropia. There's a slight astigmatism here, just half a diopter. We a little bit go on axis here. We cannot do it completely, but around 70 degrees to reduce it even more. And so we expect to have something like this, maybe a slightly myopic refraction even when we look at the astigmatism with a 20 diopter lens. In the same patient, we also did Pentacam AXL measurement before, and but we used for the calculation the IOL master. This is a measurement which doesn't really look much different in terms of the individual numbers, just slight changes. A little bit different here also in terms of the astigmatism, 0.8 instead of 0.5. But we have to really look into that if that has an impact. Well, patient on the right eye came out not bad. Uncorrected distance visual acuity 0.8, 20/25. Well, on this, and the near also 0.8, which is fine, uncorrected. If you look at the corrected visual acuity before, we were somewhere at 1.25 and 1.0. So he has lost 2 lines. And he was slightly hyperopic, plus 0.25. And we're here 3 months post-op. So this is final refraction. With that, he came to 20/20. What would have been happened if we have used the measurement of the IOL mask of the Pentacam? Now, interestingly is the 20 diopter lens with the calculation of the Pentacam AXL Wave would have resulted in 1/4 of a diopter hyperopia. With HIGUS, with SFKT, even with hover Q and holiday 1, we were ending up plus 0.16, 0.14 or 19. So the Pentacam would have predicted that outcome, and the Pentacam would have suggested another lens, a different lens, the 20.5 diopter, which then may have resulted in 1/4 of minus, which I think would be easier for the patient to be accepted than the other way. If we look at the other eye, interestingly, the right eye here, we had a little bit more astigmatism and at 71 degrees. The IOL calculation also with the Pentacam seen here, and then with the IOL master, we calculated trifocal toric. Spherical equivalent was 20/75, and the lens was plus 20 combined with minus 1.5, as you can see here. Here we had a very good outcome. Uncorrected distance visual was 20/20, uncorrected near 0.8, which is also fine. And we would have the same measurement here with the Pentacam. Here they were in agreement if you look at the spherical equivalent. So IOL calculation here would have been the same. But as I said, interestingly, with the IOL calculation here, on the other eye, we had 1/4 of a diopter offset. So when we look at all these things, we have done extensively clinical tests and really did a lot of quality control in the analysis, very promising results for almost everything that we have measured, total spherical aberrations, subjective refraction for phakic, pseudophakic keratoconii, all the parameters supporting premium IOL selection show a very high repeatability and standardization. And we can use this really prior cataract, refractive surgery, any corneal surgery, and also to solve some of the mysteries. I get a lot of referrals where patients are unhappy and we can exclude a lot of things and differentiate. Do I have to exchange the lens, or is this a corneal problem here, or whatever? So we can do a lot of things with the Pentacam AXL Wave. With one measurement, we get enormous amount of information. So if we go back to the initial question, is it worth the investment? I would say yes, of course. It's a win-win situation. So with the Pentacam AXL Wave, we're really talking about the future, so to say, the next generation and the best of both worlds in the diagnostic area. And I'd like to thank you very much for your attention.
Professor Auffarth, thank you very much for this presentation, which gives a comprehensive overview about the work that you did with the Pentacam AXL in the University of Heidelberg.
Very welcome.
Yes, a few questions came in, and we will use the remaining minutes to try to get them answered. One question was, what is the difference between the Pentacam AXL and the AXL Wave and the resulting benefit for you?
Well, I think I have shown that quite nicely in some of the examples, that we can measure not only the total wavefront, that we can really split the eye in the different optical parts, and then can differentiate where is a problem. We have the corneal wavefront, we have impact on the lens or on the cataract or on the photophakic lens, and then we have the total wavefront. And some measurements, for example, with the Pentacam AXL, you could measure, or you could extrapolate and calculate corneal wavefront. Yeah, so we had already that information, but we didn't have the total wavefront measurement. And this is an integral to, it's a really a very, very big positive impact here, because with the corneal wavefront alone, you have no idea to tell anything. For example, if you correct an astigmatism or something, or even corneal aberrations with an intraocular lens, because you only measure the cornea and you don't get any feedback from the whole system. So this is very, very important actually here, and makes this machine a true wavefront analyzing machine.
Thank you. Another question is, and I think you also showed this in one slide, but maybe not everybody got it. When you implanted a toric IOL and you want to check the position regarding axis and orientation, is this now possible with the new Pentacam AXL Wave, and how would you use it?
Yeah, so what we can really say is that we have several features. I may actually see if I can show you the slide here. I think it was more or less at the end.
Yep, it was.
Somewhere here, let me see.
Slide 74.
I think here somewhere. First of all, what you can see here very nicely is we have an astigmatism with compromised vision. We have a corrective agent, an implant, and at the end, we have a very good image. So this already explains that the thing is in the right axis. Then we have the ritual illumination photo here. We see also here the marks lens. We see the tomography here, and the other picture here can also show it direct. Oops, show it directly to you. Here are somewhere the marks. So here's a mark, and you know that the correction is always 90 degrees away. So you can really very nicely see how a toric lens is correcting. What we don't see on this image is that we also have the feature of looking at tilt. Yeah, because we have a shine flux system, and we see if a lens is not really straight in the eye. So the tilt function is also interesting, because this can induce or cause some problems. For example, one haptic is in the sulcus and the other is in the capsular bag, and this is a very bad thing if you have a toric lens. Yeah, so machine gives you several features to do that.
Yes.
The total refraction will give you an idea about that.
Yeah, perfect. Thank you. And One question came in, and I do not really know why this was asked, but one attendee asked, have you checked the ratio between the spherical aberrations in the 4 versus the 6 millimeter zone yet? If there's any correlation, any offset, any shift?
Well, we haven't done this specific analysis. I really have to think about why I should do that. What information would it give to me? Because the larger the pupil, the more has it an impact on also repeatability and all this kind of stuff. So, the visual quality, maybe the night vision is interesting here, but a normal person doesn't run around with 6 millimeter dilated pupils. It could be an interesting, let's say, academic question if we can see from the difference, can have any kind of information that will help us to interpret the quality of the data. It's interesting suggestion, I would say. We may actually look into that and see if we have some problems in 4 millimeters. How does it look in 6 millimeters or so? So yeah, maybe we should look into that, but we haven't done it for this study.
Yeah, thank you. And another question that maybe I can answer from the company is maybe easier. One attendee asked regarding the Olsen formula. The Olsen ray tracing formula is part of the IOL calculator, is available in the Pentacam AXL and in the Pentacam AXL Wave. And if you do not have it yet, just contact your distributor that you get the latest software update, and then you have this formally also available. So when I now look, there are no further incoming questions. So everybody stay safe and healthy. Goodbye and have a nice weekend.